What's poppin', dogs? Mr. Allen here for the final review video for the Algebra 2 Honors Finals review. We got Module 3, Topics 2 and 3, right? We're going to merge them together into one. It's going to be dope. All right. Now, this is like the fourth time I've tried to record this video. Things been happening, whatever. We're going to get in on this one, man, all right? No more interruptions. Okay. So we're going to determine whether each function is exponential growth or exponential decay. Now, we want to look at our base, right? The number that's being raised through that exponent. For the first one there, it's 2/3. So that's between 0 and 1, which means it's going to be decay. Now, this next one here is 3 for my base, which would make us think growth. But that negative in the exponent is a horizontal reflection. So instead of going like this, when we reflect it horizontally, now it's going to actually look like this. So that's going to actually be a decay function. So decay once again, all right? That horizontal reflection or reflecting over your y-axis causes it to become a decay function. Last one, I have 10,000 times 0.5 raised to the x. That 10,000 is a distraction there. It's the 0.5 raised to the x that will cause this one to once again be a decay function. Oh my goodness, 3 decays in a row. Did you really think we were throw that at you, man? Keep you on your toes, dogs. Keep you on your toes. Now that part B there, if it was just 3 to the x, that would have been a growth one, right? Okay, next thing. So we got a town's population is growing continuously at a rate of 5.8% annually. In 1990, the population was 12,500. How many people are likely to be living in the town in the year 2030. All right, let's set up an equation here. So this could be your A pert or N nert. They're really the same thing. When we're talking population, you'll often see the N version of this formula, N not E to the RT. Let's fill some things in, right? So my initial population is 12,500. We've got E is just E, right? That's like 2.7 something. Raised to the, my rate is 0.058. Don't forget to change that rate into that percentage into a decimal for my rate. And how many years are going to pass? Well, from 1990 to 2030, that's going to be 40 years. All right, so the annual growth is 5.8%, and it's being compounded continuously. All right, let's make sure my calculator's up. It looks like it's good. Okay, cool. Just always do a little software check here. I'm going to clear this out. I've clearly been mathing, right? So we had 12,500. Then we have E, which is second natural log. Then we have 0.058, the lights went off, times 40. So times 40. Let's see what we get here. We got ourselves, all right, 127,195.9. So let's say 96. 127,196. I forgot already. There we go, 127,196 roughly people, right? That's what the model is predicting there. And I would have rounded up, that's just me personally, the 195. Some people will even just say like, oh, it doesn't quite get to that other person there, so we'll keep it 195 instead of 196. Either way, as long as you're showing that work, we Gucci, right? If it's a multiple choice question, we're not going to throw 195 and 196 for our last 3 there. We're not going to put that. That would just be rude, right? Okay. So next one, the population of Riverdog Jennytown was 120,000 in 2019 and is growing continuously at an annual rate of 7.1%. Based on this model, what will the population be in 2026? So same kind of idea here, right? So we've got ourselves N of T, or in this case, in 2026, that's going to be 7 years, right? N of 7 equals, we got 120,000 E to the 0.071 times 7, because that's going to be our T, right? We can plug that all in. So we got 197,200, and I'll say 54 people in Riverdog Jennytown. Now, the next one's a little different. When will the population reach 500,000 or 500,000 people if this growth continues? So we're assuming the same growth situation here, right? So I'm going to have 500,000. Got to get all my zeros there. There we go. Equals 120,000 E to the 0.071 T. And I'm going to solve this thing for T. So the first thing I got to do here is divide by 120,000 on both sides. 120,000. I'm not even going to really worry about, it's 50 over 12. What would that be? 25 over 6. We could write that. Not a big deal if you don't do that, but I guess I will. 25 over 6 here equals, and then we've got E to the 0.071 T. Now, how do we get rid of that E right there? Well, if I take the natural log on both sides, so natural log and natural log, These two right there undo each other. They don't really cancel. They're just inverse functions of each other. But in any event, they are gone, okay? So now we're going to pop up here. And I've got the natural log of that 25 over 6 equals, and I've got 0.071 t. I'll divide by 0.071 on both sides to get t, right? So right now, I'm going to throw this entire mess into my calculator. I have the natural log of 25 divided by 6, close my parentheses, divided by 0.071, hit enter, and we've got ourselves 20.1 years. So 20.1 years. All right. So it says, when will the population? Well, I guess at that point, so we do 20 years added onto that 2019. So that's what? 2039 in the year 2039. 2040, right, between that time frame there would be when we're going to experience that situation, that population rather. Okay, there we go. So I added that onto the 2019. Good to go. Cotton Eye Joe. I don't know. All right. Anyways, number 4. Okay, let's go. All right, next one's here. We got write the following geometric sequences as functions with an exponent n. We did like a couple of these in this particular unit. Not a lot of them, but it's okay. All right, so a quick reminder of exponent properties. If I have like bases, I add my exponents together. So here's what's going to happen. All right, I've got 3 times 10. I can break this apart to 10 to the nth times 10 to the negative first, okay? I'd add those together. If you need a little side math here, here's what I'd have. If I had like a to the 4th times a to the, let's say, 6th, I'd add them together, I'd get a to the 10th. The same would go as if I had a to the, let's say, 7th times a to the negative second, I'd get a to the 5th, right? We're just going like in the reverse thing here. It looks a little different, but that's the property that we are using there, okay? I'm going to go ahead and just erase this up because people won't know what that means on the key. They'll be like, bro, what is this side math? All right. So now 10 to the negative first, this light timer is just fantastic. So 10 to the negative first, I can just do the reciprocal. It'd be 1/10 or move it to my denominator. So I'm going to have 3 over 10 times 10 to the nth power. Now I have an exponent of n. We are good to go. Whee, boom. Awesome. All right, same kind of process on these other ones here. So again, I'm going to have 2 times, and we'll have 6 to the n times 6 to the negative first. Now I will do 2 over that 6, right? Because I can move that to my denominator times 6 to the nth. And what's 2 over 6? That's just 1/3 times 6 to the n. And now it looks more like one of your like exponential equations, right? Definitely looks like that when it's not an n minus 1. So geometric sequences is something that many will experience in Algebra 1, and then refresh it here when we are in our exponentials unit. All right, last one here. I'm going to just pause it, write it out, so feel free to try it on your own. And there we have it, folks. We have 4 times 2 to the n, and that is just absolutely magnificent and wonderful. All right. Let's continue, dogs. Let us continue. And, I apologize for the, lackluster audio and video quality on this one as far as my face is concerned and my voice. I don't have my big old setup of like my microphone and my fancy camera. So we just rocking, what you call it, stock, right? Stuff. Okay. Number 5 here. Let's continue. Which of the following is the graph of the inverse of f of x equals 2 to the x? The inverse of f of x equals 2 to the x is log. So f inverse of x equals log base 2 to the x. However, it might even be easier not even thinking about what the inverse function is. Let's think about some points, right? On f of x, okay, and I'll do this over here. So on f of x, if we had x, we had f of x. If I plugged in, let's say 0, I'd get 1, right? 2 to the 0 is 1. If I plugged in 1, I'd get 2, and if I plugged in 2, I'd get 4. On my inverse, I'm looking for those swapped. So 1 comma 0. Well, they both have 1 comma 0, right? This one has 1 comma 0, and that one has 1 comma 0. What about 2 comma 1? Let's see here. 2 comma 1 is not on that graph. We have ourselves a winner here. So this one would be f inverse of x. Now, obviously, the other one's going to be the g of x, but let's talk about y. So if I have x and we have g of x, right, it's going to be log base 4 of x is my inverse of g of x. But again, kind of easier to work with the t-chart here. If I'd have 0, I'd get 1. And then if I plug in 1, 4 to the first power is 4. 4 to the second is 16. So which one's going to have 1, 0? We know they both have that. But how about 4, 1? I see it right there on this graph, 4, 1. So this one's going to be g inverse of x. There we go. I like it. Good stuff. Good stuff. Okay. Let's go. Let's continue. Let's keep pushing along here, dogs. Almost done. Almost done. All right, we got given the graph of f of x equals log base 3 of x. Find our domain, range, y, and blah, 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 blah. Okay, all sorts of dope stuff, right? Domain, okay? This is log base 3 of x. I can't have negatives. I can't have 0. So my domain is going to be x is greater than 0. Or you could write it as 0 to infinity. Those are two different notations meaning the same thing. All right, range. So my range here keeps going down, keeps going up as it goes to, you can't see my finger point, as it goes to the right, find my little cursor there, it keeps going up. So my range is all real numbers. Now, if you think about exponentials, our exponentials, the y is greater than 0, and the x is all real numbers, right? It flip-flops. They're inverses of each other. X's and y's swap. Now, in interval notation, if your teacher prefers that, it's negative infinity to positive infinity. I don't really care. I like whatever's cleanest. So in my opinion on this one, I would use x is greater than 0 and y is equal to all real numbers. Plus, I love writing down that bougie double stick R, right? It just, I feel so dope, right? That's sad that makes me that happy, but you know, it does. Okay, anyways, y-intercept. It never crosses the y-axis, does it? Nope. All right, so none. Does it ever cross the x-axis? Yes, it does. Where is that at? It's at 1, 0. So 1, 0. Don't be fooled by the grids, right? Look at the scale. The scale is important. How about an asymptote? Yes, it has a vertical asymptote. Sound effects necessary at x equals, or of x equals 0. It's a vertical line, so it's x equals. How about my end behavior? So as, let's see here, my end behavior is as x goes to, as it approaches 0, right? So as we're approaching that asymptote there, that vertical asymptote, what's it doing? So as x approaches, and we're going to have 0 from the right-hand side, right? We're coming from the right-hand side. Then f of x, that's approaching, let's see here, it's approaching negative infinity, right? Okay, I'm not leaving myself much room. All right, now, got a little more room. As x approaches infinity, as x approaches positive infinity, what's it doing? It's going up and it goes to the right. Hopefully you can see my pen cursor. Then we have f of x is going to positive infinity. Yay. All right, last thing. Given the function g of x equals f of x plus 3, which of the following would change? Which of the above would change? Well, that's a horizontal shift to the left 3. So let's write that down. Left 3. That's what that's doing right there. So what would change? Well, if I shift this graph to the left 3, now my graph is over here. Well, actually, that's way over here. Like my vertical asymptote would be that. And my graph would look more like something like that, right? I don't know exactly where it's going to cross. Well, I kind of do. One sec here. So I'd have something like that one there, a little green action, right? So this is x equals 3. So let's see here. Let's go through all of them. This is light. We're just trying to make math videos here, right? And the lights keep going off. Anyways, so let's top down. Domain. Domain's going to change, right? So domain would be, that'd be x is greater than negative 3. How about my range? Range doesn't change, okay? Range does not change. Y-intercept, it looks like we actually do have one now. It would occur, let's see here, it would occur actually at that point right there. Not something we'd necessarily ask you for. That's a little bit trickier to get, but it is on here, so I am doing it. Our Y-intercept would become 0, 1. If we plug that in, if I plugged in 0 for x, I'd be evaluating that function at 3. Log base 3 of 3 is 1. That's how I would know that for sure. Okay, but we could also find another point and shift it. For example, on my initial one here, 3, we have 1 right here. If I shift it 1, 2, 3, I'm at 0, right? So there are ways to do that one, but a little bit tricky. How about x-intercept? Yes, we already have that down there, right? We said x-intercept is going to be now at 2, right? So negative 2, 0. What about my asymptote? Absolutely. Vertical asymptote, that's going to be x equals negative 3. End behavior. The only thing that's going to change here, is as x approaches -3 from the right, then we have f of x approaching negative infinity. So it's only this part right here. This is the only part that is changing, right? We're only going to -3. Not a major change. Okay, that's the only thing there. The big ones to look out for are like, does my asymptote change, right? That's a big one that we can ask you for. Or does my domain change here, okay? The same would go for asymptote or range with an exponential, right? That's the main thing we're going to ask, but, you know, bonus points for doing the other ones because that was dope math. All right, let's see here. Solve. My goodness, we have a whole bunch. Okay, let's get it popping. We got to loop and swoop this bad boy. Loop, swoop. There it is. That was awesome. Equals 64. So I'm going to take the 6th root or raise to the 1/6 here, dogs. Raise to the 1/6. You know, I love rational exponents, right? It's great. It's way easier than like going into your calculator, right? So now I'm going to have n equals 2. All right, the 5th root of 32 is 2. The 6th root of 64 is 2, right? I don't know why I decided to bring in the 5th root to this mix, but I did, right? All those 2's you should know up through like to the 6th power, okay? 2 to the 1st, 2nd, 3rd, 4th, 5th, and 6th, for sure. All right, next one here. I've got 1/2 raised to the -3rd equals n. So 1/2 raised to the -3rd equals n. Negative exponents don't give us negative numbers. They give us reciprocals. So let's think about it this way. Really what I have here is 2 raised to the +3rd, reciprocal, equals my n. That's a big equal sign. There we go. And so we get 8 equals n. Beautiful. All right. So again, reciprocals, not roots. Doesn't give us negative numbers. Awesome. All right, next one here. We got 10. So log base 10 of 1/1000. Loop it. Swoop it. There it is. 10 to the n equals 1/1000. 10 to what power would give me 1,000? It'd be 3. So 10 to the -3rd gives me 1/10,000, or 1,000, excuse me. All right, cool. Next one, we got 2 to the x plus 1 equals 2. So, like x, or like basis, right? 2 to the x plus 1, 2 to the 1st. So I'm going to get x plus 1 equals 1. I get x equals 0. Nice. Nice, beautiful. And if you plug that back in, you'll see it does work because I'd get 2 to the 1st, which is 2, plus 3 is 5. All right, now, here we go. Okay. We can go into log form. Let's see here. Or we can think about what to the 4th power would give me 16, because then that same thing to the -4th power would give me 1/16. And if you're thinking it's 2, n does most definitely equal 2. 2 to the 4th gives me 16. 2 to the -4th gives me 1/16. Next one. I got n. Oh boy, you guys loved these back in the day. So we got n to the 3/4 equals the 4th root, or I'm going to write 8 to the 1/4. 1/4 right there. And now let's see here. I love rational exponents. What if I raise both sides here? Raise both sides. Come on, marker, work. To the 4/3. Okay. Because if I do that, what happens with those guys right there? That just becomes 1. So I'm just going to have n equals 8 to the, well, the 4's are going to cancel. 8 to the 1/3. Oh my goodness. What's 8 to the 1/3, or the cube root of 8? That's going to be 2. Man, you know, when in doubt, I just say throw down a 2, bro. That's 3 of them where n equals 2, right? Highly likelihood, it seems like that. High likelihood. All right. Now we got some logs, dogs, logs and properties. I got to condense the left-hand side here. So I'm going to have a log that's base 10, right? It's 7 times 2 is 14x equals 4. Now I'm going to loop it, swoop it. I got 10 to the 4th equals 14x. All right, and then we've got what? That's going to be 10,000 then. 10,000 equals 14x. We'll divide by 14 on both sides. We'll get that x. Now, if you didn't know that one right there, right, I'll even double check. 10 raised to the 4th power. You can always throw it in your calculator. This would be on the calculator portion here. There we go, and we'll divide by 14. And we can either write it as a decimal that we're going to get here, or if you hit math and you choose frac, it'll change it back into a simplified fraction, which is 5,000 over 7. Let's do 5,000 over 7 over 7, and we had our decimal there. It was 714.29. 714.29. All right, either one of those would be Gucci. Okay, let's see here. Next one. Ooh, I'm going to do 8 to the negative third here. So 8 to negative, third equals x. So 8 to the third power. Well, 8 times 8 is 64, but then that gets that's kind of a bit, right? So I'm just going to do it to the third, and the reason being is then I can just throw it into a fraction myself. We get 1 over 512 then, all right? 1 over 512 equals x, and we'll leave it as a fraction for that one. Oh my goodness, another one of these. I love these. They're great. Loop it, swoop it. I'm going to pause it for this one, let you guys, work it. And we got 32 to the 1/5 power, or the 5th root. Oh my goodness, it comes back. It worked out that I talked about that, the 32 and the 5th root is 2, right? Because there we go. Now we knew. You're like, bro, I knew that because you mentioned that earlier when it seemed pointless, but it wasn't. All right. J here. So 7 to the 2x minus 3. I'm just going in the dark right now. I wonder how it looks. I can't even see. It's all right, right? I like the other side, the math. We're doing math right here. Okay. 343, I'm pretty sure, and I'm just going to bust up my own TI right here. 7 to the third power is 343, that is. So I'm going to go this route. I'm going to say 7 to the 2x minus 3 equals 7 to the third. You could have also looped and swooped this thing, right? And then that would be just fine. But now I can set my exponents equal. 2x minus 3 equals 3. And then I'm going to add 3. I get 2x equals 6, divide by 2. And I get x equals 3. Nice. Next one, I'm going to divide by, I know we're going fast here, dogs, but I got places to be. I got to leave here in like 5 minutes. Oh, my goodness. Divide by 10. I end up with 2 over 5 to the 5x minus 1 equals 5. Now, I'm going to loop and I'm going to swoop this bad boy. So we're going to have log base 2/5 of 5 equals 5x minus 1. So in case you don't know how to do this, right, I'm going to pull up that calculator. I hit math, alpha, math. I can type in that 2 divided by 5, arrow over 5, hit enter. Then I'm going to add 1, and I will divide by 5. So do the last bit of algebra myself here. Negative 0.151, so x equals negative 0.151, or just 0.15. Okay, nice. So next thing, I'm going to add 6 here. We got 2 times 3 to the negative 4x equals 46. Divide by 2. I get 3 to the negative 4x equals 23. And then we got log base 3 of 23. I'm going to loop it, fin about to swoop it, equals negative 4x. We could plug that in, right? We're going to hit math, alpha, math, alpha, math. We got 3, arrow over, 22, hit enter. And then we're going to divide this bad boy by negative 4. So negative 4, enter, negative 0.7. All right, x equals negative 0.7. Oops, don't forget that negative. There we go. I don't often throw zeros in front of my decimals, but I decided to today, right? Because I was feeling it. All right, it's time to talk transformations now, dogs. We have our log functions here. We got to identify the transformation in each function. So the first one's log base 2. So what's different from log base 2? Well, it has a negative out front, and if it's outside the function, that is a vertical reflection, or we're going to say reflect over the x-axis, right? If I'm doing a vertical reflection, I'm going over the x-axis. So either one's cool if it's free response. However, if it is on a multiple choice, you have to be able to identify them. Generally speaking, we'll say reflect about the x-axis or reflect over the x-axis. One of those two will work. Now, the other one we have inside the function, we are subtracting 5. We got to think opposite on the inside, so it's going to be going to the right 5. Beautiful. Next one, we have log base 5 of x. Now, it doesn't matter that our log base has changed. The reflections, the shifts, transformations all work the same. So first thing we're looking at there is the negative that's on the inside of our function. So if it's a negative on the inside, it is a horizontal reflection or a reflection over my y-axis. See, if I'm moving my hand, I would be moving my hand across that vertical axis, which is the y-axis. That is a horizontal reflection. Now, how about that 4, right? We're looking at it as a 4, not as a negative 4. The negative is the reflection. That 4 is a stretch or compression. Since it's on the inside of the function, we got to do the reciprocal, which would be 1/4. So it is a horizontal compression by 1/4. And then lastly, we have that -1 on the outside. Since it's on the outside, it is a vertical shift. It's going to go down 1. Going down, yelling timber. Very good. Okay, I'll never not say that joke. Okay, down 1. Beautiful. Last one here, we have log of x. If there's nothing written there, it's log base 10, remember. Not important for this one, but always a fun fact, right? So it's log base 10 of x, and then we have 5 times log base 10 of x. Well, it's just that vertical stretch, right? It's on the outside, so it's vertical stretch by 5. Ooh, that's a terrible B. There we go. By 5. Lovely. Fantastic and wonderful. All right. On to these. You guys loved these on your quiz and test. I think these are just fantastic problems. All right. So suppose that log base a of 3 equals r, log base a of 6 equals s, and log base a of 5 equals t. Write an algebraic expression for each. This would be a multiple choice question for sure. So let's see here. Well, 18, the way that we think about this is, how can I make the argument, which is 18, out of these 3 numbers here with multiplication or division? Because once I have multiplication or division within my argument, I can expand it to addition and subtraction. And then I can have a sum or difference of the r, s, and t. So let's do that. Well, 3 times 6 would give me 18, right? So I'm going to write log base a of 3 times 6. That's in my argument of that log. Multiplication expands to addition. So I'd have log base a of 3 plus log base a of 6. Well, what's log base a of 3 equal to? It equals r. What's log base a of 6 equal to? It's s. So I now have an algebraic expression for each one of these in terms of that r, s, and t. Nice. Next one. We have 1 over 10. Oh my goodness. Fractions, bro? You serious right now? That's not cool. How in the heck can I get that? Well, we're not going to get 1 over 10 outright because we have no 1 or 10. But what if I multiplied 6 and 5? That's 30. And what if I did 3 divided by 30? That would simplify to 1/10. So that's the move we're going to make. We got log base a of, we're going to have a fraction here, a little bigger. We got 3 over 6 times 5. Right? That would be 3 over 30, which simplifies to 1/10. So this is an equivalent log expression. Now I'm going to break it apart. We got log base a of 3. We have minus log base a of 6. And then what about that log base a of 5? Would it be addition or subtraction? It's going to be subtraction because we're dividing by that 5. I could have done 5 times 6 or 6 times 5, right? So it's not like just because the 5 is second, it's going to become addition, because if I swap the 6 and the 5, then the 6 would become addition. That doesn't make sense, right? So they're both going to be subtraction because I'm dividing by both. The way I place them in the denominator is, I could have done either one, 5 or 6, right? So they're both going to be subtraction because I'm dividing by 6 and I'm dividing by 5. That's the key there. If I'm dividing by that, it's going to be subtraction. So now I've got log base a of 3, which is r, minus the s there, and then minus t. And there we go. We have our next answer. That's so exciting. So wonderfully exciting. All right. Just checking on Jenny right now. She's chilling out on the deck. It's actually a lovely little morning here before I got to go in for a curriculum development at district office, which doesn't start till 8, but I got up at the same time. I was like, you know what? I'll make some math videos, right? Okay. Well, I also just wanted to finish this up. So log base a of 90. We kind of need these guys up here still. Oh, there we go. All right. So log base a of 90. I got to get 3, 6, and 5 to give me 90. Well, we did say that 5 times 6 is 30. What if I multiplied that by 3? That's 90. There we go. So that's what we're going to write up. So we got 3 times 6 times 5 is 90. And now since they're all multiplication, I can break them all up into addition. Excellent. So we have all of them expanded out, right? It was multiplication, turns to addition when we expand. And now I just have my log base a of 3 is equal to r. And we have log base a of 6 is equal to s. And then we have our t. Nice. All right, this last one here. Again, another fraction, bro. We're just throwing some at you here. That's exciting stuff, right? So I have log base a of 18 over 5. Didn't we get 18 in the first one there by doing 3 times 6? I divide that by 5. So we got log base a of 3 times 6 divided by 5. And that would be all in my argument. And now I can break it apart into addition and subtraction, right? When I expand this thing. So I will have addition for the first 2, subtraction for that 5 right there. And now I can go ahead and replace them with their particular variables. So log base a of 3 is r plus s minus t. Excellent. Only one of those on your final exam. But, you know, having a little bit of practice there, that's a dope, right? So a lot of times these final exam reviews, this is not like the distribution of the problems. We might just add more of the difficult ones, the ones you guys struggled with in the semester. We'll add more of those to the review so you can get a little more practice, right? So don't think that there's like, oh my God, there's like 4 of those on my exam. No, all right? But I think you got that now. I think you got that. It was scary at first. We got it now. All right. We got to expand these expressions here and then evaluate if possible. It's not always possible, but sometimes it is. All right, so the first one, log base 3 of 8 times x cubed divided by y to the 7th times z. So we're going to have addition when we expand the numerator, subtraction when we expand with that denominator, right? Because we're dividing, so it becomes subtraction. All right, so we've got log base 3 of 8. So I'm going to need some room here. Log base, it's a terrible G to start. There we go. Log base 3 of 8. And then we have log base 3 of x cubed. But I'm going to bring that, I guess I can just write it out. We'll write it out the first time. For this one, I'll show a little more work. Log base 3 of x cubed. Man, I struggle with the 3s sometimes, man. There we go. That's a nice 3. Then we got minus log base 3 of y to the 7th. And we have minus log base 3 of z to the first. No exponent there. All right? So it's to the first. Now I'm going to evaluate if possible, and I'm going to move those exponents of the argument, right? It's x cubed, it's y to the 7th. We're going to move those out as coefficients. So log base 3 of 8, I cannot evaluate that by hand, right? So we're not going to do a decimal or anything like that. If it was like log base 2 of 8, then it would be 3, right? Because 2 to the 3rd power equals 8. But it's not, so we're leaving it. So plus, then we got 3 log base 3 of x, and then we have minus 7 log base 3 of y, and then minus log base 3 of z. And that will be our fully expanded, I kind of ran out of room there, fully expanded, wonderful logarithmic expression. Beautiful. I also fixed the box. It was irritating me, you know. All right. Next one here. We got, oh boy, we got a whole lot. We got x to the 4 over 2. I think that was a typo, but that's okay. We'll leave it. Okay. So that's just 2, right? We got log base 8 of, let's see here, log base 8 of 64 plus log base 8 of x to the 4 halves. I'm just going to change that to a 2 right now, right? We're going to change that to a 2. And then we have minus log base 8 of y to the 5th and minus log base 8 of z to the 7th. Now here, we're actually able to evaluate. Log base 8 of 64, 8 squared is 64, so that is just 2. Then we have plus 2 log base 8 of x minus 5 log base 8 of y minus 7 log base 8 of z. There we have it. That's beautiful. That's fantastic. Hopefully no mistakes so far. But if I make a mistake, make sure to shoot me an email, find me in the hall and be like, Mr. Allen, I think you made a mistake, bro. And maybe a screenshot of the timing of when it is. And I'll check it out. And then if you are right, bro, I'm going to hook you up with a Yoro sticker, maybe just high five. If I got any extra candy, which I don't use, well, I have some Twix, but those are mine, right? I'm going to eat them. So Yoro stickers. All right, now that we've expanded, we're going to go ahead and condense now into a single logarithm, right? So when I do this, I like a big old fraction if I see any subtraction, right? So I'm going to go right ahead with a log base 5, big old fraction, open up my parentheses, right? And that first one there, that coefficient of 3 is going to go up to an exponent with that x. So I will have x cubed in my numerator. Now, I have subtraction here, right? And it's 1/4. And then we have log base 5 of y to the 16th. Well, if I take that 1/4 and I multiply it to that 16, that'll become 4. I'm going to show that in a couple steps here. But we'd have y to the 16th to the 1/4. We'll clean that up in a sec. And then the last one, I have positive, so plus 6 log base 5 of z. That's going to go up as an exponent, so z to the 6th. And since that is positive, that is going to be z to the 6th up here. All right. If it was subtraction, it would go to the denominator. The first subtraction sign does not have any bearing on that last term there, the 6 log base 5 of z, because it's not going to be distributed, right? If there were parentheses around that and you had to distribute the negative, then yeah, the z to the 6 would be in the denominator. But that's not the case. So last thing here, my final answer, log base 5 of, we have x cubed. I want a better 3. Oh my goodness. 3. Then we got z to the 6th over, and 16 times 1/4 is just y to the 4th. Nice. There is my answer. All right, next one we got to, oh boy, just numbers. Now, we get so used to variables now, I feel like sometimes we're scared of numbers, right? We'll be okay. We'll be okay. All right, it's all log base 9, right? It's all log base 9, so we can condense it into a single logarithm, as the directions ask us. We have some subtraction, so I am going to throw in a nice little fraction here. We got, it's going to become 2 to the 6th. I'm just going to write that down, 2 to the 6th. Then we have 4 to the 3rd. All right, and then last one here I have times 8. Oh boy. Now, you could throw this fraction into your calculator. We'll do that, but I'm going to go do this by hand as well because I feel like crazy like that. Okay, ready? So we got log base 9, because this would be a good non-calc problem, but this is me on the multiple choice. We got 2 to the 6th. I'm going to keep that. And then I got 8 would be 2 to the 3rd, right? Over. Now, 4 to the 3rd could be written... I'm really struggling with these 3's, man. 3. We could write that as 2 squared to the 3rd, which would be 2 to the 6th, right? So I'd have 2 to the 6th right here. Now, in this scenario, these would cancel, leave me with just 2 to the 3rd in the numerator. But say they didn't, I could have put my exponents together. I'd have 2 to the 9th in the numerator over 2 to the 6th in the denominator, which would leave me with 2 to the 3rd, right? So I'm going to have log base 9 of just that 8. That'll be my final answer right there. And I could have done that with my calculator. I will show you guys. If I hit alpha and then we hit the x right there, it gives me that nice fraction. I'd have 2 raised to the 6th, and then I'd have 2 cubed, or just 8. We can really just do times 8. Actually, I want to make sure that's going to multiply times 8. I think it would by default, but I'm not sure. And then we have 2 to the 6th, or in this case would be... Yeah, it was just 2 to the 6th. Couldn't remember. All right, there we go. Boom. Enter. And we get 8, right? Or I guess it would have been 4 to the 3rd initially. All right, cool. Either way, you get 8, so it's log base 9 of 8 would be the correct answer. So make sure you're simplifying in there. Beautiful. All right, time for a little solving, and I think that's it, dogs. We got 4 problems here. 4 problems, and we're done. That's perfect, because I got to get going here in a sec. All right. So I got 2 logs on the left-hand side, no logs on the right-hand side. I'm going to condense the 2 logs. If I got 2 logs on one side, I'm always just going to condense them in a solving situation here, and then we'll proceed possibly in 2 different ways. So first thing here, I got log base 4 of x squared plus 6x. I'm multiplying my arguments, right? So I'm going to distribute that x into the parentheses of x plus 6. Then, because I only have 1 log, I'm going to swoop. Those colors are too similar there. I'm going to go with a green here. Loop, swoop. All right. And then I'm going to have 4 squared equals x squared plus 6x. So I got 16 over here equals x squared plus 6x. And now we panic because we're like, bro, I've never seen a problem like this before. Oh, wait, you have. It's a quadratic. We set this bad boy equal to 0. We factor. It's my favorite thing to do, right? Factoring plus 6x minus 16. So what multiplies to negative 16 and adds to 6? Nothing, right? Oh, no, wait, we're wrong. It's 10, and it is negative. Wait, not 10. I'm talking too much. 8 and negative 2. There we go. Anywho, I know what I'm doing with stuff. Actually, I don't need another equal sign. We would have x plus 8 equals 0, so x equals negative 8. And I have x plus, not plus, x minus 2 equals 0, so I'm going to have x equals positive 2. Now, do they both work? Well, if I go back to my original, if I throw a negative 8 in for x, that first log, this first guy right here, that's going to be log base 4 of negative 8, which is not allowed, by the way. You can't have a negative argument, so that's an extraneous solution, whereas this is an okay solution. And I think I've said it before, but just in case you forgot, right? An extraneous solution comes from proper algebraic steps, right? Solving the problem properly, the correct way of solving it, but the answer does not work in the original problem. Great multiple choice question. If I were writing a test, which I did, I might ask that question. All right. Next up, we have x equals 2. I did box that without saying, but if I plug 2 in positive arguments, it will work out beautifully. All right. Next one here. We have log base 8 of x plus log base 8 of x minus 2. And then, we have a log on the other side. But still, like I said, I'm going to condense those 2 logs. We got log base 8 of x squared minus 2x. Kind of similar start. But now, because I have a log on both sides, I'm going to be able to use the one-to-one property of logarithms, right? And I'm going to have, that 8 was supposed to go, there we go. Okay, I wanted a better 8. That's minorly better. All right. So I have log base 8 on both sides. I can cancel, not cancel, but, well, I guess it's kind of like canceling, right? It's the one-to-one property. So boom, gone, boom, gone. All right. If my logs are the same on each side, then my arguments need to be the same on each side. So we can just set our arguments equal to each other and solve from there. Same kind of idea as like if you have like bases of exponents, then we can set our exponents equal to each other. All right. So we have x squared minus 2x equals x plus 10. I'm going to subtract, bring everything over, set it equal to 0, just like we did in the last problem. So I have minus 3x minus 10 equals 0. What multiplies to negative 10 and adds to negative 3? Well, that would be what? Negative 5, positive 2. I like that. I'm into that. That's dope. So we get x minus 5 equals 0, x plus 2 equals 0, and we got x equals 5, and we have x equals negative 2. Now, do they both work? None of them work? One of them work? Well, if I plug in the 5, I got 5 for one argument, I got 3 for the other, I got 15 for the other. I'm cool with that. If I plug in negative 2, it does not work in 2 of them. Regardless, if it doesn't work in one of them, it doesn't work. So extraneous solution. No! All right. Beautiful. Fantastic. It does work sometimes. But generally speaking, when we have 2 solutions, a lot of times one of them is going to be extraneous, the other one's not, but not always the case, okay? When we're talking about logs or any other function that has a domain restriction, right? So if we have a radical function, there's the chance for extraneous solutions because I can't have negatives inside my square root. If I have rationals, I can't have a 0 in the denominator, potential for extraneous solutions. Logs, I can't have a negative argument, potential for extraneous solutions. But here, as we come into exponential equations, no domain restrictions. We Gucci. All right. So I'll pick blue for this one. All right. First thing here, I'm going to divide by 2 on both sides. And now I have 9 raised to the 4x minus 3 equals, what's 54 divided by 2? 27. I'm going to do this non-calc style, but you could loop and swoop right here if you'd like. But I'm going to do it where I write equivalent bases, just in case we decide to throw one of these on your non-calc. I don't know. Maybe. We'll see. All right. So we got 3 squared to the 4x minus 3 equals 3 cubed. And then let's see here. I distribute my exponents. So I'd have 3 raised to the 8x minus 6 equals 3 to the third. So now I can set my exponents equal because my bases are equal, just like we did with the logs in the previous problem. I'll have 8x minus 6 equals 3. I'll have 8x equals 9 after I add that 6. So divide by 8, and I get x equals 9 over 8. Yay! Dope. Okay. Last one here. Actually, you know what? Let me just show you guys how we would do that if you decide to go with your calculator. All right. So when I'm at the point of, I'll write off to the side here. When I'm at the point of 9, this step right here, 9 to the 4x minus 3 equals 27, I could do log base 9 of 27 equals 4x minus 3. And I could throw this bad boy in the calculator with a little math, alpha math. So math, alpha, math. I get 9 right there in the base, 27 as my argument. I get 1.5. We're going to add 3, right? So add 3, enter, divide by 4, hit enter. And then if we hit math and then frac, I'm going to get 9 over 8. Same answer. Cool? So you could go through that one with your calculator if you so choose. I prefer doing it by hand, but I don't know. I'm weird, right? Okay, cool. Lovely, fantastic. Let's see here. Boom. All right, last one here, guys. Last problem. Last math problem of the semester here. It's an emotional time, yes? All right, so I have 1/2 to the x squared plus 4x equals 8. Again, I'm going to do this by hand because I'm crazy like that, you know? Bit of a math baddie, if you will. So we got 2 to the negative 1, right? That would be 1/2. That's 2 to the negative 1. Then I got x squared plus 4x equals, and that's 2 to the third, right? So now I'm going to have 2 to the negative x squared minus 4x equals 2 to the third. And then I can set my exponents equal just like we did before. So I got negative x squared minus 4x equals positive 3. I'm going to set everything equal to 0. But I'm going to bring everything to the right-hand side because I want that x squared to be positive, right? Do not try to factor with a negative leading coefficient. It's It's actually impossible, kids. It's impossible. I've never seen anyone do it correctly. You know, not even Elon Musk can factor with a negative lead coefficient. I have no idea. But it seems like everybody always screws it up, so I just say don't do it. All right, what multiplies to 3 adds to 4? That's going to be 3 and 1. So x plus 3, and we have x plus 1. So I'm going to get x equals negative 3 and x equals negative 1. I didn't feel like writing them out equal to 0. I decided to just skip a step because I'm crazy like that. All right, I've said that a lot. Beautiful, fantastic, and wonderful. Let's see, actually, what would you do? I think what you could do here is if you were to loop and swoop, you'd have your math alpha math, math alpha math. Our base would be 1/2 or 0.5, right, of 8. And if you hit enter, you're going to get negative 3. So we would get right to, let's see here, we'd get to x squared plus 4x equals 3, right off the bat, okay? So if you wanted to loop and swoop, that is viable, right? We'd have, let's see here, I'll do it off to the side here, one sec. If we wanted to loop and swoop, you could have had log base 1/2 of 8 equals that x squared plus 4x. And then you'd have the negative 3 here equals x squared plus 4x, and we'd end up with the same situation, right? So either way, slice it is going to work. Totally up to you guys. I'm going to do it by hand in those situations because they do often show up in a non-calculator setting. That's it. That's dope. I thank you guys for watching these videos if you've made it this far, and I hope you crush your final exams rather than be crushed, right? And I bet you if you watched all 4 of these videos and you're doing the bonus videos that I'm going to make a playlist for you guys, then you shall crush your final and not be crushed. That's it. Deuces, dogs.